Hello there, and a very warm welcome to you all. My name is Ken Weller, and I've spent a fair few years tinkering in my workshop, utterly fascinated by the hidden forces that make our world tick. It's a place filled with wires, strange contraptions, and the constant gentle hum of discovery. Today I want to share a little piece of that magic with you, something that feels like it's been plucked straight from the pages of a science fiction novel, yet it's as real as the workbench beneath my hands. We are going to explore a delightful phenomenon, one that connects the worlds of temperature and electricity in the most elegant of ways. It's a principle that allows us to create cold with a simple current, or even more excitingly, to generate movement from nothing more than a bit of heat. This journey begins not with a bang, but with a quiet observation. Imagine holding a small peculiar device in your hand. You connect a simple battery to it, and within moments one side of the device becomes astonishingly cold, perhaps even forming a delicate layer of frost. Meanwhile, the other side grows noticeably warm, radiating a gentle heat into the air around it. This isn't some sleight of hand. It's a fundamental property of our universe at play. It's the sort of thing that makes you stop and stare to simply wonder at the sheer ingenuity of nature's laws. It feels profound, doesn't it? To command temperature with such directness, using only a trickle of electrical energy to separate hot from cold. What we are witnessing is the core of what I want to talk about today. This effect has quietly powered some of the clever gadgets in our lives, from portable camping coolers that keep your drinks chilled without any moving parts, to specialized scientific instruments that require precise temperature control. It's a silent, solid-state hero, working away without the clatter of compressors or the whirring of fans. And while its ability to cool is impressive, its hidden potential is even more captivating. For within this simple act of creating a temperature difference lies the secret to making things move, to building an engine that runs on the gentle dance between hot and cold. So I invite you to settle in, perhaps grab a cup of tea, and join me on this little adventure. We are going to peel back the layers of this fascinating effect, looking at how it works in simple, everyday terms. There will be no baffling equations or impenetrable jargon, I promise you. Instead, we'll use our imagination to see how a temperature gradient, a simple difference between a warm side and a cool side, can be harnessed to create a continuous rhythmic motion. We are about to unlock the magic behind a thermoelectric motor, a true wonder of engineering powered by the Peltier effect. It's going to be a brilliant journey. So, what exactly is this Peltier effect I keep mentioning? Let's break it down. At its heart, it's a love story between electricity and heat. Imagine you have two different types of metal, or more commonly, two types of semiconductor material joined together in two places to form a complete loop. When you pass a direct electrical current through this loop, something quite remarkable happens. One of the junctions where the two different materials meet starts to absorb heat, making it feel cold. At the very same time, the other junction releases that heat, plus a little extra from the electrical process, making it feel warm. It's a heat pump with no moving parts. Think of it like a conveyor belt for heat energy. The electricity you apply acts as the motor for this invisible conveyor. As the electrical current flows, it forces heat to be picked up from one spot and dropped off at another. If you reverse the direction of the current, the whole process flips on its head. The junction that was cold now becomes hot, and the one that was hot becomes cold. It's this beautifully simple and reversible relationship that makes the Peltier effect so wonderfully versatile. It's not just a one-way street. It's a dynamic, controllable system for moving thermal energy from one place to another. To make it even clearer, let's use an analogy. Picture two different types of escalators side by side, one going up and one going down, representing our two semiconductor materials. The people on the escalators are like the electrons in our current. At the bottom, where you step from one escalator to the other, you might need a little push, absorbing energy to get on the up one. At the top, as you step off, you might release a bit of energy. The Peltier junctions are like these transfer points. At one junction, the electrons have to absorb energy from their surroundings to make the jump to the next material, which cools the junction down. At the other junction, they release that energy, heating it up. This isn't some newfangled discovery either. It was first observed way back in 1834 by a French physicist named Jean-Charles Athanase Peltier. He was a humble watchmaker turned scientist who noticed this strange temperature anomaly when running a current through a junction of two different metals. For a long time, it remained something of a scientific curiosity, a neat trick, but not terribly efficient. However, with the advent of modern semiconductor materials, its potential has been truly unlocked, allowing us to build powerful modules that can create significant temperature differences, all from this elegant, fundamental principle of physics. Now we arrive at the truly exciting part. We've established that applying electricity to a Peltier module creates a temperature difference. But what if we reverse the process? What if, instead of supplying electricity, we supply a temperature difference? This is where the magic really begins to happen, and it's all thanks to a related phenomenon called the Seebeck effect. Essentially, the Peltier and Seebeck effects are two sides of the same coin. If you heat one side of our special semiconductor junction and cool the other, the device will generate its own small electrical voltage. It turns heat directly into electricity. So picture this setup in my workshop. We take two of these Peltier modules. On the first one, we create a temperature difference. We could place it on top of a warm mug of tea, while the top side is kept cool by the surrounding air. As we just learned, this temperature gradient will cause the module to generate a small, continuous electrical current. Now we take that current and feed it directly into the second Peltier module. And what happens when we feed electricity into a Peltier module? As we know, it creates its own hot and cold sides. It becomes a heat pump. Here's the clever bit that creates the engine. We arrange this second module, the motor module, within a magnetic field. The electrical current we are feeding into it flows through the semiconductor materials. And as the laws of electromagnetism tell us, a current flowing through a magnetic field will experience a force. This force gives the module a tiny push, a little nudge. By designing a rotor that holds magnets and arranging our current-carrying module correctly, this continuous push can be translated into a continuous rotation. The heat from the tea is creating a current, which in turn powers an electromagnet that drives the motor. The result is a beautiful silent engine that spins with a quiet grace, powered by nothing more than the warmth of my drink. It's a symphony of physics in motion. The temperature difference on the first module generates a voltage. This voltage drives a current through the second module. The interaction of this current with a magnetic field creates a force, and this force creates rotation. Every part of the cycle is seamlessly connected, transforming a simple temperature gradient into elegant kinetic energy. It is a stunning demonstration of how these invisible forces can be harnessed to create something tangible and truly wondrous. What we have here is more than just a charming desk toy or a fun experiment to show your friends. It's a window into a future where we might harness energy in a completely different way. Think about the vast amounts of waste heat generated all around us every single day. Car engines, factory chimneys, power stations, even the back of your home refrigerator, they all pump enormous quantities of heat into the atmosphere, energy that is simply lost. A thermoelectric generator based on this very principle could capture a portion of that waste heat and convert it directly back into useful electricity, improving efficiency and reducing our reliance on other fuel sources. The applications are truly mind-boggling when you start to think about them. Imagine self-powered sensors for remote locations, perhaps in the Arctic or a volcano's crater, that use the natural temperature difference between the ground and the air to power themselves indefinitely. Or consider medical implants, like pacemakers, that could one day be powered by the natural heat of the human body, eliminating the need for batteries and replacement surgeries. We could even see this technology integrated into our clothing, creating wearable electronics that charge themselves as we walk around, powered by our own body heat. Of course, the technology still has a way to go. The efficiency of current thermoelectric materials is still relatively low compared to traditional engines or power plants. A lot of the heat energy is still lost in the conversion process. However, scientists and engineers all over the world are working tirelessly to develop new materials and more ingenious designs. They are exploring nanotechnology and complex alloys to create semiconductors that can convert heat to electricity with far greater efficiency. Every small improvement brings us a step closer to a world where these silent, solid-state generators play a significant role in our energy landscape. And that, in a nutshell, is the astonishing power locked within the Peltier effect. It's a journey from a simple temperature difference to a whisper-quiet motor and potentially to a cleaner and more efficient future. It reminds us that there are incredible forces at play all around us, just waiting to be understood and harnessed. I hope this little exploration has sparked your curiosity as much as it continues to spark mine every time I see that little fan spin. If you enjoyed our journey today and want to see more wonders from the workshop, please do give this video a like and don't forget to subscribe. Thanks for watching.